So welcome to this tutorial, Numbers and Logic Together in CP. Simon and I wanted to present the state-of-the-art of cost function network algorithm as implemented in Toolbar 2 and give you a description of the algorithm for solving the weighted constraint satisfaction problem, but also how it is feasible to learn cost function network from historical solutions using a tight connection between cost function network and stochastic graphical models. So what is a graphical model? Informally, it's a description of a function of many variables as a combination of a set of simpler functions. And this is used in many areas to describe various types of function, and it has two interesting properties. It's concise because we use a set of small functions, and it allows nevertheless to describe a complex object because we describe a function of many variables that whose value results from the interaction of several small functions. Typical functions that you may be interested in, for example in SAT, you want to describe a digital circuit, and the function would be the value of the output of the digital circuit. In CP, a schedule, and the starting date, and would it be feasible, or is it acceptably late? And we use it for from the chemical composition of a molecule, which is a discrete object, to compute its energy, for example in protein design. We will use the following notation. So variable are uppercases, maybe indices. The domain with d to the x notation, and this for indexed variable. Lowercase are values, uppercases and lowercases in bolds represent sequences or sets or lists of variables or values. And the domain of a sequence of variable is just the Cartesian product of the domain of the variable in the sequence. So the elements of these sets are tuples. Tuples which define an assignment of the variables in the sequence X. And this tuple can be projected to a subset Y, and this is the notation. Now we can define a graphical model more formally. We want to describe a function. The function maps tuple to some objects that will be member of a set B. And the description of the function is made from the combination of small functions. So to combine these small functions, we will need an operator O+. And with this, we can define a graphical model, sequence of variables, then each variable has a domain, and then we have small functions or factors. Actually, each function is denoted as phi. It has a scope S, which is a subset of V, and it maps tuples to elements of B. And we have the usual notion of scopenarity. And with this, we can define the join functions, which is just a combination of all those small functions. This is a mathematical definition. If we want something more implementable, we must choose a language to describe the functions. And in this tutorial, we will assume that the functions are described as multidimensional tables. What is fashionable to call tensors now over the set B, of course. If your variable are Boolean, you can choose to use instead weighted clauses, B-weighted clauses. So as usual in SAT, maxat. And if your set B is numerical, you can use arithmetics or polynomials. And of course, you can use a specialized language if you have specific functions in mind. Examples for constraint networks and SAT. You have a sequence of domain variable. You have a set of Boolean functions because essentially you are defining what is a solution or what is not a solution. So a solution will be considered as true and a non-solution as false. And then it's very simple. The join function will be the logical conjunction of all these small functions which emit Booleans. And that's it. You have defined constraint networks and SAT, well, or let's say CNF formula at the same time, just changing the language for functions. Now, let's shift to a purely numerical example, just to give some contrast. A stochastic graphical model called Markov random fields. You have the usual variable and function, but this time the functions are numerical and they emit non-negative real numbers. And then you combine all those small functions using the product. That is, the joint functions will be again a non-negative real function. And you want to construct a probability distribution from this, and what you have to do is take this joint function and divide it or normalize it in some sense to be sure that it's a probability distribution. And the only caveat is that this normalization constant is sharply hard to compute. Now, the last graphical model we will see in this tutorial, the one we will play maximally, I would say, cost function networks. Again, we have variables and functions, numerical functions again, but this time they will be non-negative integers, and this strange notation is just here to denote the set of integers bounded by k, which should be given, and k can be finite or infinite. It can be infinity, but it just denotes the infeasible assignment here. So that if at some point the cost of an assignment reaches k, it means that this assignment is infeasible. So it's an upper bound. And to combine the functions, we use this operator, which is bounded addition, simply to have an internal operation. So the joint function is simply the sum, the bounded sum of all functions, as this small k indicates here. Inside the solver, we assume that we have a constant function available in the set phi. And also we assume that for every variable, we have a unary function, phi I for simplicity, associated to every variable. And it is used to represent information available on each domain. So for example, the fact that some value u of xi is mapped to k by the unary function means implicitly that the value u can be deleted. And this has nice properties. The first property is that this phi empty set here is a lower bound on the joint function because we have only non-negative functions, so by summing up things can only increase. And the second one is this k, because we can easily recover constraint network or SAT, depending on the language, by using k equal 1, because in this case we have only two costs available, 0, which represent true, and 1, which represent false. It's unusual, but with this we have plus 1 is equal to the zoological conjunction. So we have constraint network inside. This can be used, for example, to represent this simple min-cut problem. Imagine you have a graph and a weight on the edges. You can represent every vertex by a Boolean variable, which says on which side of the cut the vertex is. And then you have a function for every edge, and the function will take cost w, the weight of the edge, if and only if the two vertices are on different sides of the cut. And for hard edge, of course, you can use the cost k. For this simple graph, for example, you can use this cost function network. So this is a microstructure. This is one variable. Inside the variable, you have two vertices, one for each value. And there is an edge between two values if and only if there is a function that connects the two variables and the cost which is given to this pair is different from 0. So this is the opposite of the usual microstructure in constraint network. So 0 cost, authorized pairs are not represented. Only forbidden or somewhat forbidden pairs are represented. This is how the problem is represented in one of the many formats that Toolbar2 accepts. In this case, it's JSON compatible. Now we have functions, we have graphical model, and we want to say a few things about them. So we're interested in two properties, very simple properties. We will say that two functions or two graphical models are equivalent if the functions are always equal. And the name equivalent is nice because it corresponds exactly to logical equivalence if we use Boolean costs. So the two functions are equivalent because they have the same truth table in this case. And for a more numerical aspect, we will also use relaxation. So we'll say that phi is a relaxation of phi prime if it is dominated by phi prime. And again, this has a nice logical interpretation, because in the Boolean case, when k is equal to 1, being a relaxation means that you are semantically entailed by the other function. So that has a nice logical interpretation. So now, we have cost function network and graphical models. We want to do optimization. What do we do in practice? Well, if we use Boolean and clauses, minimizing is solving that problem. If you use tensors instead of clauses to express your functions, you are actually solving the constraint satisfaction problem. And if you use a more extensive numerical scale, like this set here, and tensors, you are actually solving the weighted constraint satisfaction problem. If you see, you can always use the same operator all along, so in the rest of the tutorial we always use this operator. It can be logical or numerical, it works the same. Obviously, those problems are all NP-hard or decision NP complete. You can try to solve them using ILP. With many assumptions, this is an example of an ILP encoding for binary functions only, weighted CSP, and pure optimization. That is, we assume that k is equal to infinity and that all functions are finite. In this case, we can encode the WCSP as follows. We take a Boolean variable for every value of every variable in the model, which says that this value is used. And similarly, we have a variable that says if a pair of value AI and bj is used, then this y must be true. Obviously, if you use the pair, you must pay for the associated cost. And if you use a value, you must pay for the associated cost, and this is the criteria to minimize. Now, what are the constraints? You must use exactly one value per domain. This is direct encoding in some sense. And then if you use a pair, you must use the left part of the pair, of course, to be consistent, and the right part of the pair also to be consistent, and vice versa. If you add this integrity constraint, this encodes the pure optimization side of the WCSP. If you forget this integrity constraint, you have an LP, which is very famous, and which is called the local polytope for the WCSP problem. This is the ILP way, pure optimization ILP way, but what about the CP way? CP is tree search plus local consistency. So let's start with tree search. To define tree search very simply, we use a first operator on functions. When you do tree search, you assign variable with value. So for example, you assign x with a, and it has an effect of functions. It reduces their scope, and we denote as this the conditioning, the change in scope of the function as we assign a variable. So an example is here. Imagine you have a function of two variables, x1 and x2, and you know that x2 is equal to b. Then conditioning means that you reach a new function which depends only on x1 now, and the table is just this subtable. So it's a very efficient operation. We are just moving a pointer inside the table. And with this, we can define the tree search very simply. Essentially, how does it work? You choose a variable v that has a non-singleton domain. You choose a value u in its domain. And you reduce your optimization problem to two sub-queries, one where you condition by the assignment, and the other one when you remove the value. And you do this recursively, inductively, you get two answers, you return the minimum of the two answers, because you want to minimize. Obviously, at some point, you will get only singleton domains, and in this case, the minimum is obvious. There is only 1 point, and you can compute its cost and update the upper bound to this cost, because you only want to find solutions which are better than this. So this is really a new upper bound, and you update k like this. To improve this algorithm a bit, you can do branch and bound, and you can use a lower bound, such as phi empty set, and the global upper bound, such as k, and when these two bounds meet, you simply prune, and you stop searching in the current branch. This is already not naive, it corresponds to partial forward checking, and forward checking in the classical case. But if the tree is too big, you can do partial search, only partially explore this tree. You can either relax the pruning rule, which still provides some guarantees, or you can bound the number of backtracks or the number of discrepancies with an heuristic assignment, as in limited discrepancy search in CP. Should we explore these three depths first or best first? Well, actually, Toolbar 2 uses an hybrid of these two. We do depth first search for a fixed amount of backtracks. And when the amount of backtrack is reached, there are pending nodes on the right of the tree, in some sense. These pending nodes are simply extracted and pushed onto a list of open nodes, and then we restart depth first search from the best open node in this list. So we are doing depth first search and best first search at the same time, and this algorithm is very nice because it is also tree decomposition friendly. I will not detail this, but for this type of problems, you can have guarantees, computational worst-case guarantees that are better than the traditional exponential guarantee of tree search. This algorithm has other nice properties. Because it does these DFS probes, it provides good upper bounds quickly. And because it does this best first search, it can produces an improving global lower bound. So it gives an optimality gap as Cplex or ILP solvers. These DFS probes provide implicit restarts, and they also offer an easy way to parallelize. Now, if HBFS cannot solve your problem, you can go to local search, of course. Here we describe a VNS, variable neighborhood search. We start with an assignment, a given assignment of the variable, and we select a subset of those variables, a subset of fixed size S. And on these small sub-problems, we use some optimization algorithm, let's say partial search, for example, partial tree search on this smaller sub-problem, and we reach some assignment. And if this assignment we reach is better than the original one in terms of cost, we use this new assignment and we reset the size of the variables here, the set of variables, to an initial small value S0. If instead this assignment has not improved, we forget it and we increase the size of the neighborhood going from S to S plus 1. This is how VNS works. So now we have local search and we have tree search. We need now to recover local consistencies. And for this we need two tools, very simple tools. So the first one is combination. Combination of two functions simply means adding them together to get a new function. It's an expensive operation because we need to fill a table with tensors whose size is exponential in the scope of the union of the two scopes we want to merge. Example with a unary function on x2 and a pairwise function on x1 and x2. The union of the scope is x1 and x2, and we have a table to fill in, and we simply fill in this table by adding things together. So 5 is 1 plus 4, and that's it. And in this case, I assume that k is large. Let's say that k is equal to 10. So there is no bounding to do, but it could be done, of course. This is the first operation, so combination. The second operation is also expensive in time and space. There's always exponentials in the scopes. It simply takes into account the fact that we are optimizing, and it tries to get rid of a variable in the scope of a function, assuming that it will be assigned to its optimal value for this function. So imagine that we have a functions of two variables, x1 and x2. This was this function here. And we want to get rid of the variable x2 because we assume it will be optimized out. Essentially, for the first value of x1, the best choice is 5, which corresponds to A here. For the second column, the best choice is 6 for A again. And for the last, it is 5, in this case for C. And we get a new function 565, which only involves x1. And for each value here, it's nice to see that we have a sort of witness or support, I would say, for this. The argmin of the elimination, here it's value c for this 5. And we can eliminate x1 from this function. We get a constant function, which is equal to 5, because this is the minimum of all those three numbers. And we, for example, could choose the third value as the argmin of this, or the support or witness for this. These two operations are expensive but powerful. Combination loses no information, of course, everything remains equivalent. Elimination loses a bit of information, but it preserves optimality, because we assume that x1 will take its optimal value. And these two operations are actually at the core of two important families of operation: local consistencies and unit propagation in SAT, when we apply this operation on sub-problem induced by one non-naive function. And if we apply reason instead on sub-problems which are defined around one variable, so a variable plus all the function that connects this variable to the rest of the problem, we are instead looking to variable elimination and the resolution principle. The nice thing is that elimination, it computes a minimum, so it produces a relaxation, which means it produces implied information in the Boolean case. Let's see how it works. For example, how we can describe R consistency, the good old R consistency, the one of constraint satisfaction problem, using these two operators. Essentially, in the pairwise case, we take a pairwise function, so pairwise constraint, and we take a domain of the variable, xj, which I said is represented by the unary function. We combine them together, and usually we say we project it. The equivalent operation is elimination here. We eliminate the variable from which we took the information domain. It produces a new function, which is called a message, usually in the stochastic graphical model side. And this message is a function of x on xi. And because it was produced by elimination, it's actually a relaxation of the original function, so it's implied by in the logical sense. And because it's implied, this message we can add it to the domain of the variable xi. That is, if we have proved, for example, that value has cost k, we can delete the value u from the domain of phi. So this provides the usual R consistency mechanism. We can define an associated properties when the message produces no new information, and all message produce no new information. We know it has a unique fixed point that can be reached in polynomial time, in linear time actually, for table, for tensors. And this has this notion of support for a value which is nothing but the argmin of the elimination that is done here. That's our consistency for CSP. If we want to do the same thing for cost function network, how can we do this? We cannot do exactly the same thing. It does not work simply because numbers add up. So 1 plus 1 is 2, and things get crazy, you lose equivalence, and you get a meaningless result. So you have to do something to preserve equivalence, and the idea is simple, although it took some time to get it. We will simply define an operator of subtraction that cancels out with the bounded addition, and the definition is easy. And we will compute the message as in our consistency. We will add it to the domain of phi, and then, so not phi j, and then we will subtract it from its source using this operator. It seems useless, adding and subtracting, but actually the cost information moves from large scopes to smaller scopes. And in the end, we can hope that it will reach this empty scope, so it will improve the lower bound. And this is actually what can be achieved in practice. So this is an example with two variables. usual things. This is an edge that is assumed to have cost 1, like other edges here. And this one here just means that we assume that we have a unary cost function on x1 that gives cost 1 to this value, cost 0 to this one, since there is nothing. Now we can decide to eliminate x1 from this binary function. We will add the message to x2 and subtract it from the function, and we get this. So the cost has increased to 1 by adding the message, and these two edges have disappeared because we subtracted this cost. Obviously, if you swap plus and min, you go the other way around and you go back to this problem, and you can now decide to eliminate x2 instead and add to x1. And you get this problem. We have added a 1 here because this is our new message, and we have removed these two edges because we have subtracted. And of course, again, we can swap and go back to the center problems. But another thing that would be more interesting to do is we can notice that here we have a 1 for both cases. And so instead, we can decide to eliminate this variable from the unary function here. And in this case, we produce a message that has an empty scope. And this message says that the lower bound can be increased by 1. And this is safe if we subtract from its source. So we get this equivalent problem. So here we saw 4 different problems. They are all equivalent. And obviously this one is nicer because it has a non-naive lower bound. We also see that things can cycle easily. So it looks like R consistency, but it preserves equivalence, but there are maybe many fixed points. Eventually, possibly there may be no fixed point. So things have to be taken care of. And essentially all the successive R consistency take care of fixed point existence in different ways, on different sub-problems in some sense. So node consistency, R consistency, directional R consistency combined together. They sequence this operation inside very small scopes, so one function plus the unaries inside, and you must enforce a direction to avoid cycles, and this defines argmin of elimination, full support. If you schedule the operation on stars, so a variable plus all incident functions, you get stronger supports and stronger bounds. And the strongest one is probably virtual R consistency. And although it does not work this way, it actually, in some sense, enforces supports which will involve any spanning tree around the variable, around each variable. And those supports are very interesting because essentially those supports provide super strong value ordering heuristics. Because we know, for example, we can prove that support for IDAC, it satisfies the fact that it has unary cost 0, because it's the argmin and we subtract from it. When you subtract the minimum from itself, you get 0. And we can prove that it can be extended for free on the star on which you schedule the operation. And so it's a very good value to choose for assignment. VAC are even better, VAC supports, because they can be extended for free on any spanning tree. So they are even better. And the other nice property they have is that node consistency actually does some extra job, which I didn't describe. It prunes. Essentially, it checks if the constant term plus the unary cost exceed or reach this upper bound k, and in this case, it deletes a value from the domain, although this is sort of implicit, as I said before. They have nice properties. So first of all, when k is set to 1, we recover exactly the usual notion and algorithm of node consistency, directional R consistency and R consistency respectively. They are polynomial time, reasonable space complexity, even when you extend this beyond pairwise problem. Obviously, they are incremental and they strengthen the lower bound, as we saw, and there is an ordering of the strengths of those lower bounds. The remaining issue is that they may have several fixed points, and each fixed point may have a different lower bound. And so we show that trying to find the optimal sequence of operation, maximizing the lower bound is decision NP complete, bad news. But A few years later, we notice that maximizing the lower bound, if you allow for rational cost shifting operation, becomes polynomial, and this is achieved by doing two things together, essentially, which is not surprising. You will solve the dual of the local polytope, which we previously saw, and the dual variables are actually the amount of costs that need to be shifted. And you must additionally perform R consistency, so the classical R consistency, to deal with all the costs which are equal to K or reach K at some point. The two strongest local consistency, or SAC, LP-based and AC-based, and VAC, which is purely AC-based, are quite strong because they can solve three structured problems exactly as R consistency. They can also solve permutated submodular subproblem, which is very nice. I will not describe this, but for example, it solves min-cut problems, which means that VAC actually, which does not use LP, is stronger than max flow, nevertheless. OSAC is also, we saw in practice empirically quite expensive to apply. And instead, even VAC can be too expensive in some cases. But still we see that cost function network local consistencies, they are able actually to provide a fast approximate dual LP bounds. And the nice thing is that you don't have to do this mixed LP and AC stuff. They deal with constraints seamlessly. So a single principle does both the LP reasoning, LP-like reasoning, and the CP-like reasoning. This is why we can say this nice sentence. And this has practical effects. This is an example of same protein design problem, which is not permutated submodular, encoded very directly into Cplex on one side and inside toolbar 2 with VAC on the other side. You see that Cplex solves the problem in 900 seconds, and toolbar 2 on this problem is 2 orders of magnitude faster. And this is not just protein design. We have those kind words of computer vision people, so they use toolbar 2 and Cplex as a sub-solver in an higher level solver for a Markov random field. And well, this is what they say, toolbar 2 superior to Cplex in all our tests. So this works for tensors. What if we use clauses instead? So if we do partial weighted maxat, well, essentially everything remains the same because combinations and eliminations work on clauses. The only difficulty is this subtraction operation. If you subtract a clause, essentially you had to add the opposite of the clause, and the opposite of the clause you shift from a conjunctive normal form to a disjunctive normal form, but you need to remain inside the CNF language, and so you have to generate a bunch of additional compensation clauses. So this means that in some sense, this soft R consistency, they work in a simpler way inside CP than inside SAT, which may explain why toolbar 2 has often very good performances. Now, local consistency is done. Let's look to the other case. We want to eliminate a variable, and we consider the subproblem defined by one variable and all the functions that connect this variable to the rest of the problem. We can compute a message. As usual, we combine all functions, we eliminate one variable of interest, and we have this nice property which says that essentially, if you keep the message and throw away the functions and the variable, you change nothing in terms of optimality or maximum best costs in some sense. So you can do this, it's okay. How does this work in practice? So imagine you have a variable, two functions that connect it to the rest of the problem. You combine them using bounded addition. It produces a larger function and you eliminate with min. Remember, this is exponential in the size of the scopes. You get a message and you can actually do variable elimination. You get rid of the variable, you get rid of the function, and instead you use the message. This can be very expensive if you have many neighbors here. So there are strategies to deal with this. One strategy that DAO to use is to split this set in subsets. In this case, you only produce lower bounds. Toolbar 2 does not do that, but it uses a simpler strategy where when you have a variable with a bounded degree, you actually eliminate it here, like this. You also do this. And you do this not only at the root node, but during tree search at any point. And if at some point you reach a problem where no variable have small degree for whatever value of small you want to choose, then you decide to condition. So you assign this variable, different ways to assign it, but this will, by conditioning, reduce the scope of all those functions, and you will reach, depending on the conditioning, 3 different problems but with the same structure, and you can solve each of them just by elimination, successive elimination. And essentially on those problems that has around 10 variables, you only need to do one branching. Everything is efficient otherwise. So that's boosting search with variable elimination, Javier La Rosa. I haven't time to describe all the bells and whistles inside toolbar 2. You saw that we have nice value ordering heuristics. We have traditional variable ordering heuristic, but also recent VAC-based heuristic by Fulya Trusser, PhD student in the team. You can do dominance analysis called substitutability in constraint network and dead-end elimination in Markov random field. You can decompose function at the root nodes to reduce scopes. You have actually global cost functions, so the equivalent of global constraint bus will cost like weighted regular decomposable or non-decomposable one based on flow algorithm, thanks to a collaboration with Jimmy Lee and his students in Hong Kong. You have incremental solving and guaranteed diverse solution, the work of Manon Ruffini, especially useful for protein design. And if HBFS cannot solve problems, you can use a sophisticated variant of variable neighborhood search that I will quickly describe. Essentially, it combines the idea of variable neighborhood search, where your neighborhood increases when optimization fails, with an increasingly strong partial search, so a limited discrepancy search. In the end, you solve the complete problem because all the variables and maximum discrepancy. So the method is complete, but it actually can find the optimal solution sooner, even prove optimality before reaching this final problem. So it's a local search technique, but that can prove optimality. Toolbar 2, it's open source. The nice thing now is that you can use adjustable precision arbitrary sign decimal costs. You can use minimization or maximization. Of course, you have constraints available, and you have a Python API. And Simon did this huge benchmarking work using problems from really various origins. So not really only our problem. Markov random field problems, computer vision problem, our usual cost function network problem, also max CSP problem, maxsat problem, and CP problem where the criteria is decomposable. And these were encoded in various formalism, MRFs, WCSP, Cplex or ILP problems with 2 encodings. This one is the local polytop one. Same thing for partial weighted maxsat, and this one resembles the local polytop one. And also G-code using minizinc encoding for those problems that could be easily encoded in G-code. And this is a very dense representation of the result of the subset of problems where the CPU time are not negligible, so sufficiently hard. And this is time, and we normalize time for all executions. And this is the upper and lower bounds which are available, normalized around the best upper bound found by any of the solvers. And you can see that toolbar 2 behaves quite well. You can also see that here it's maxHS for maxsat, produce nice lower bounds, and that Cplex is better, which is surprising, with the direct encoding than with the tuple encoding, which is the local polytop encoding. So we went beyond that. On protein design, we compared toolbar 2 with super optimized simulated annealing implementation, and we're able to show that this simulating annealing implementation was losing optimality increasingly as the instances were becoming harder. So people from Rosetta retuned the simulated annealing, and they were very kind because now they know toolbar 2. So they compared toolbar 2 here with their upgraded simulated annealing algorithm and D-Wave, the quantum annealer, quantum computer from D-Wave, on problems of increasing sizes, and this is the CPU time. Logarithmic scale in both cases. And this comparison is of course a bit unfair because here we have an optimality proof, and here obviously we have only upper bounds. And we can see that toolbar 2 is still quite efficient compared to D-Wave, and actually it will take some time. Roughly D-Wave will probably need 20 times more qubits because this is the maximum number of, the maximum size that D-Wave can encode. So it will need 20 times more qubits probably to reach the performance of toolbar 2. And for very different job, because toolbar 2 provides a proof of optimality. Instead, D-Wave, it's still not close to optimum 90% of the time. This is a fixed gap because there is a unit for the energy unit in kilocal per mole. So, as I said, the local search inside toolbar 2 VNS is still complete, and it does not behave as well as HBFS or Simplex, but it is able to prove optimality in many cases. This is a cactus plot with CPU time here and the number of solved instances here. So it does produce optimality in a very large fraction of cases. But where it really shines is on upper bounds, of course, and here you can see how it compares to HBFS, to DAO-opt, to Simplex, and even to libdi, which is a very famous Markov random field library. And if you have many cores, it performs even better, of course. Now, this is it for toolbar 2. I just wanted to show you how we can learn CFN from data, thanks to the connection with the probabilistic graphical model. So what do I mean by learning CFN from data? Imagine you have a set of assignment of the variables which come from some high quality solution distribution you have, let's say historical solutions, and you want to learn a CFN that represents well these high quality solutions. Well, you can use this connection between MRF and CFN, which is very easy to understand. MRF use product for combination, cost function network uses sum, and you can shift from one to the other using minus log x transform, which is very usual in Markov random field and which provides so-called energy-based Markov random fields. And this connection is nice because you can, in some sense, directly reuse algorithms which have been developed to estimate Markov random field using the maximum likelihood principle. And the likelihood of a set of historical solutions is just the probability that this assignment will be produced by the Markov random field. And a nice idea which has been explored in Markov random field, which has good properties, to try to find a Markov random field which gives this set of assignment a maximum probability. And if you do simple maths, you can show that if you maximize log likelihood on the MRF, you essentially do this on the associated CFN. You want to minimize the cost of the assignment, which is consistent with the idea that they are high quality. And at the same time, you want to maximize the soft minimum of all the assignments, of the cost of all the assignments. So you are giving a lower cost to the high quality assignment, which makes a lot of sense if you want to learn a cost function network from data. And so we have a paper in CP2020 that shows how this works, how it can learn, for example, to play the Sudoku, going from a training set up to a learn CFN, including constraints, just from data. And if you're interested, you can go to this session on Friday. Thank you very much.
Okay, welcome to this second part of the tutorial on cost function networks. It will be a practical exercise using the toolbar 2 solver, and we will model and solve problems, various problems in combinatorial optimization. So I invite you to go to this web page. Where you can find a description of the toolbar 2 solver. You can download it from GitHub. There is a documentation, the user manual, and also the various input formats it can read, such as the CFN format that we will use. But there are also others, such as the probabilistic graphical model UAI format or the MaxSat WCNF format, or even the pseudo-Boolean optimization format OPV. So now let's go to the tutorials. I will present 3 combinatorial optimization problems. The first one is the weighted Latin square problem. The second one is the frequency assignment problem with polarization, which was the subject of the RODEF challenge in 2001. And the last one is the block modeling problem. During my tutorial, I will do some comments, and they are all in this script, so you can find the commands and the output of the command you have, also with some text to explain what is done. So the first thing is to install toolbar 2. You have 3 possibilities. Either you have a Debian Linux distribution, so you can install the package just doing this command, or you download the source from GitHub. So I will do this. So when you get the source, you will have to install a few libraries that toolbar is using, and then using the CMake to compile it. So I go to the main directory toolbar 2 and do the CMake command, adding MPI option and also XML to read the XCSP2 old format. Okay, so now I can compile, and here I will use 20 cores for that. And at the end, you should get a toolbar 2 executable and put it in your main toolbar 2 directory. I will do this. If you don't find all the associated libraries, you can still compile toolbar 2 with just the GMP dev library and without the CMake by going into the subdirectory source and doing the following commands. So at the end, you should get the executable as me, and if you type the name toolbar 2, then it gives you the list of options the solver has, and also the various formats it can read. Okay. So my first problem is the weighted Latin square problem. This is a problem on the chessboard n by n, where you want for every cell to choose a value between 0 and n minus 1. And each row and each column must be a permutation of the n values. We add an objective function so that for each cell there is a cost associated to any of the possible values. For instance, this is an example of a solution for a 4x4 square example. The large numbers correspond to the assignment, and the small numbers correspond to the unary cost, and the red cost is the one corresponding to the chosen value. So if you do the sum of all the red costs, you got 45, which correspond to the optimum for this problem. I will use the CFN format to model this problem. So here, for this example, the CFN format, yes, it's JSON text file format, and you have three main sections: the problem, the variables, and the functions, the cost functions. In the first section, this inferior to 64 means that it is a minimization problem, and I want to find a solution strictly less than 65. Then you give the 16 variable names with their domain size 4. And next, the cost functions. So here it corresponds to the soft or different on the following scope. So the first line corresponding to the first line in your chessboard. And the parameters are the violation measure for this soft global cost function. Here it is a variable based, and the default cost is 65. It means that this constraint is in fact a hard constraint. I cannot violate it. So the same for all the lines, all the columns. And then here are the unary cost functions. So for each cell variable, the associated table of cost corresponding to the different value assignments. So if I want to generate this model for any size, I will use a Python script. So here you can download the script. It is using a Python object, which is a dictionary, and thanks to arrays we can build for the range, for all the rows, for all the columns. We will build the dictionary corresponding to each constraint or cost function. And there is a simple function within the script to transform this object into a CFN file format. So let's see on the shell. So I copy this script and execute it with 4, so I get the following output. I can save it into a file and now solve it using the toolbar to solver. It reads the 16 variables with the 24 cost functions, and you see the initial lower and upper bounds. The upper bound corresponds to the one in the file, so the 65, and the lower bound has been produced by soft local consistencies. And for the soft diff, it corresponds to a mean flow max, a mean cost max flow algorithm. So then a first solution is found, and indeed it is exactly the same cost as the lower bound, so we have a proof of optimality on the solver end. If we want to see the solution with the names of the variables and their assignments, or we can use the following script. to have a pretty print of the solution. So I go here and use a simple awk script for that. Okay, so now how many solutions there are in the problem? I can use option -A, and I see there are 576 solutions. How many optimal solutions there are? So for that I give an initial upper bound of 36, so I want all the solutions less than 36. And indeed there is just one. I can also look for a sequence of diverse solutions. And if I copy this line, I ask to find at most 10 solutions with diversity constraint, a Hamming distance of 16 here. So it means I want completely different assignments. So of course there will be only 4 indeed. So the 4 are here. The first one corresponds to the optimal solution, and then this is the best one with respect to the distance, so of 16 between the two solutions, and so on until I have found the 4th solution. Okay, so let's have a look to a larger instance. So I will use 8 by 8 Latin square. So now you can see solutions occurring during time, as time passes, better and better, and also an information about the optimality gap, that is a global lower bound and the current best solution. This is thanks to a hybrid best first search algorithm that is used by default in toolbar. And at the end, you see it has reached the optimality proof. The best solution is 155 here. Okay, so this problem is quite difficult when the size increases. And I have made a comparison 10 years ago about the problem with other CP solvers like Choco and Six-Tux Prolog. And instead of the all different constraint, I replaced it by the GCC global kernelity constraint. And for the Six-Tux Prolog, it uses the GCC with unary cost, GCC with cost by region. As you see, when you increase the size of the problem, it goes rapidly high CPU time, and this is a logarithmic scale. But for this experiment, toolbar 2 with the EDAC GCC got the best result. Okay, thank you. Okay, my next problem is the frequency assignment problem with polarization. I have a list of radio links I want to establish between sites. Each link or path, you must choose a frequency, which is an integer value, and also the polarization that can be -1 or 1. You have a set of constraints. For instance, between two paths, I want the frequency must be equal or different. And also, I may have that the absolute difference between two frequencies must be greater than a given number, which is slightly less if the polarizations are different. So two numbers depending on if the polarization is equal or different. Those numbers depend on the given relaxation level L. And with smaller level of relaxation, those numbers are increasing, which means the constraint is more and more constrained. The objective function is a hierarchical objective function with 3 criteria. The first one, you want to find the minimum relaxation level K, such that at this level or higher level, all the constraints are satisfied. Then the second criterion is at the level K-1, you want to minimize the number of violated constraints of type 4. And there is a third criteria that for the rest of the lower levels, you want that the sum of the violations is the minimum. In order to model the problem, I will have only one variable per path, and it will represent both the frequency and the polarization. By doing so, I will be able to express binary cost functions and benefit from fast incremental soft local consistencies. So you can find the various input file from the RODEV challenge here or here. You will have also a description of the problem, and let's see a very small instance. Here, for instance, you have all the possible frequencies, 100 here for the domain 0. All the variables, only 4 variables, so 4 radio links. And here are the numbers. So for instance, for path 1 and 2, I want that the absolute difference of the frequencies at relaxation level 0, if the polarizations are equal, is 60. And here you see for the other levels up to 10. And if the polarization is different, it is slightly smaller numbers. Okay. So to generate the model, you will have to download this Python script here. Here it is, the main part about the model. So this is for the hard constraints. So you see it's binary constraints, and you have a table to represent the cost, which are either 0 if the constraint is satisfied, or top if it is violated. For the constraint of type 4, here it is when the polarization is equal. So if it is not equal, the cost will be always 0. Otherwise, if it is equal, if the absolute difference of the frequencies is greater than the deviation, it's okay, it's a 0 cost. Otherwise, it depends on the fixed level of relaxation that we choose. So we will not minimize the relaxation level, but we choose a given relaxation level between 0 and 10. So if it is higher than this relaxation level or equal to this fixed level, it means it is forbidden, so there is a top here. Otherwise, you have this second, the third criterion is if it is strictly at lower levels than k-1, it is only a cost of 1. Otherwise, it is a high cost at k-1 exactly. Okay, and the same for equality, when the polarizations are different between the two paths. Okay, so now let's see an example. So I copy the script and follow again my tutorial script, and indeed I would recommend to download this C program. It is the RODEV checker for your solution, and this awk script to do the job also. So compile the C code with this command and then execute this command. Okay. So I'm running the Python script to generate the model and then solve it using toolbar and check the resulting solution, which has satisfied all the constraints at level 3 or higher levels. This is what I ask here. And you see that at level 2, only one violation, and at lower levels the sum is 3 violations. Okay, so you can try to test a slightly bigger problem with 9 variables here. Example 2, with this command, and check again the solution, and the optimality proof has been obtained here. If we want to try larger instances that were used for the challenge, we need to take time to generate the CFN file corresponding model before solving them. So I have done this before the tutorial, and you can find all the instances by going to this link. So if I go there, you will get a repository of many benchmarks, cost function library benchmark, including the FAP benchmark, and you have the instances in WCSP format for some of the problems. So I come back to my tutorial. So download this instance and try with the default search of toolbar 2. So here I'm giving a 10-second time limit, and this instance, it has 150 variables with larger domains, so up to 300. And you see the solution found at 299 here, but it stops after 10 seconds. So instead of using a systematic search, I will use partial search with a large neighborhood search method. So indeed it is called VNS, so variable neighborhood search, and it's using problem decomposition. Here I'm using the min-fill heuristic, and also I will add the -A2, which says that I don't want too many overlapping clusters. So again, the time to read the instance, it is quite large, and try to solve it using this meta-heuristic, which uses a small neighborhood at the beginning, and it increases the neighborhood, here the number of discrepancies, when no solution has been found at previous level, up to 10 seconds. Okay, so I can do better. You see already it has improved a bit. It's 8-9 here, by using the parallel version of the VNS algorithm. So here. So now I run using MPI on 21 cores. There will be one master and 20 slaves. It means that the 20 slave will start from this first solution found by backtracking search algorithm sequentially, and then in parallel exploring various neighborhoods. It will find the solutions up to this one, and it stops after 10 seconds, the time limit. but I have given this option to save the best solution found here. So now I can check if this solution found is the optimal solution or not. And for that I will use the default toolbar to search algorithm. So HBFS, giving it the input solution found previously here. So you see the input solution cost correspond to what has been found previously. And also this input solution, so it will be used as an initial upper bound, and it will be used also as a value ordering heuristic, and also as a variable ordering heuristic, and this is thanks to our new VAC integrality ordering heuristic that will be presented in 2 weeks at CP2020. Okay, so it tries to solve the problem, and you see the optimality gap, which is quite small. The total number of values in the problem, the number of non-unary cost functions, and you got the optimum. Okay, here it took 1 minute to solve the problem. Depending on the solution, it can be faster. Like here, it was 38 seconds. But anyway, we were able to prove the optimality for this large instance. And check the solution is correct with the checker. And if we look at the RODEF challenge, we can see that for this instance, toolbar 2, we have found a better solution, and that the best one found by the competitors at that time. I tried for a few other instances, and toolbar 2 got always a better solution, except for the largest instance with 350 variables, where here I need more time for VNS to find the same quality solution. You can see that for this solution it was not so hard, because VNS was able to end and so to get also an optimality proof in less than 30 seconds. Indeed, it was a better solution than the one known by the competitors. Okay, my third problem is the block modeling problem. This is a clustering problem which occurs mainly in social network analysis. It was the subject of the best paper last year at CP. So the problem is, given an input graph, you want to find a partition of the nodes into k clusters, such that the interaction between the nodes in the input graph can be summarized at the level of the clusters. So it means that for the input adjacency matrix graph, G, if you order the nodes with the partition, you have blocks of 0 or 1 here, and this can be factorized by a m k by k matrix, such that when there is a 1 in this matrix M, it means the block should contain only 1, and vice versa for 0. This is a minimization problem, and we want to minimize the number of wrong edges. That is, when there is a missing edge in a block that should contain only 1, or an extra edge when the block should be 0. So this can be modeled again using a Python script. Here is the model. For that we are using ternary, so we are using m variables k by k for the factorization matrix, and the n variables for the nodes with domain size k. The objective function is represented by ternary cost functions. So for each cell of the M matrix and for every pair of two nodes, we have a ternary cost function which says that for this M cell in the matrix and for the two nodes, if they correspond to the same block and if the input edge is different than the one required by the M, then we have to pay a cost of 1, else it is 0. We also deal with safe loops, and we have added some constraint to partially break value symmetries on the node variables. So let's see on my simple example. So I copy the block model script and then I follow my tutorial script. So doing this command. For that you need to download simple math and also the awk script to pretty print the solution. Okay, so here again is the solution. So for 3 clusters with the factorization matrix and the partition of the nodes. So let's try on a more difficult example. So you will download here the political actor matrix. And here again the search occurs, and here it finds a solution of 26 and then prove its optimality. So this is for a 5 cluster problem. So it took a few seconds, 10 seconds more, and we have done a second model that you can find here. So block model 2, where we sort the nodes of the graph by decreasing out degree, and we also detect if the input matrix is symmetric. So indeed, if it is an undirected graph, to not generate all the M variables, because it will be also symmetric. So by doing so, so I just have, now I change to the block model 2 and solve the same problem again. So you see different solution that has been found, and again the proof of optimality, but twice faster. Okay, so we compare our results with the ones in the Mathnet paper, and for the small data sets, the 4 ones with the largest number of clusters here, 4, 5, 5 and 3, here are the results in seconds, and we got better results for 3 of the instances, not on political actor, but still it's much better than the default CP model or even the MIP model. On larger networks, it makes a huge number of ternary cost functions. So this is about the maximum size that our approach can perform, whereas the CP approach worked with larger networks. Still, we have another local search method in toolbar 2 that does quite well on these instances, and here you can see if I add the option -I, so using in-scope local search in pre-processing, I found the best solution directly, and then just have to prove the optimality. It was not faster here. Okay, thanks. My last example is about learning cost function network from solution data. We want to learn the user preferences based on historical solutions, and in order to make recommendation within a car configuration system. The idea is that the user select some variables to configure the car, and the system make a recommendation for the most preferred value based on previous user choices and also on the learned user preferences. So let's have a look to the Renault example, and have a look to the README. And here come the original datasets we used. So it's a project with a French car manufacturing company, Renault, thanks to Hélène Fargier. We are interested in the following product description. Medium corresponds to a small urban car, and big to a utility van with more product variability. And those product descriptions are a constraint satisfaction model where each variable corresponds to a different type of option, for instance, which engine, the color, and so on. And the constraints are the compatibilities between the options. Some of the variables are implied by the others, so only a subset of the variables are decision variables that the user must select and choose a value. So our goal is to try to predict what will be the chosen value given the knowledge of the previous user choices and the learned cost function network. So for that, we use historical data here. This is 1 year sales history. So each cell corresponds to a car configuration made by a user. So using this information, we want to make a prediction for the most preferred value for the next selected variable by the user within the car configuration system, and we want that it corresponds to some possible feasible configuration with respect to the manufacturing constraints. So we will combine our learned cost function network with the product description, the CSP, the corresponding CSP. Now for that, you need to go back to this link, and the CFN learn submodule, you have to go there, in toolbar 2, GitHub, and perform the following commands to download the source and to compile toolbar 2 module for Python, so that you can have access to the toolbar 2 library from Python. So let's go again to the README for Renault. So the main script is renault.py, and before running it, I will have a look to the complexity of the medium product. Okay, so here it is the number of solutions for the medium product, and I'm using toolbar 2 for that, with looking for all the solutions and using backtrack with tree decomposition. here you see the tree width, which is quite small compared to the number of variables, 148. Here the total number of feasible car configurations is relatively small, about 200,000. So now we can apply our Renault script to learn the cost function network corresponding to user preferences. And do an evaluation of the prediction of our recommendation system by doing a simulation of a user car configuration session. So first, using all the sales history, we use part of it for the learning part, so to learn the cost function network. And for that we are using convex optimization, which is quite fast here, and the resulting CFN has something around 300 binary cost functions. Then we will compute the precision quality of our prediction using other test samples, so the rest of the sales history. And here it is, so I go to the end. And you see there the precision at the beginning, so when you are the user has not choose any of the options, so it is already quite high precision, 81%, and then the user makes a choice, and then the system will recommend for the next selected variable what is the most preferred value, and you see the precision increases as the number of user choices are made. The problem to get the most preferred value corresponds to solving the cost function network with the partial assignment by the user choice and the mandatory constraints. This problem is never too difficult. As you can see, there is less than 200 backtracks. We have followed the tenfold cross-validation protocol to build to compute these curves. So the green curve corresponds to combining the learned model with the mandatory constraints. And this is compared to a naive Bayesian approach, which is the red curve, and to an oracle, the blue curve, which knows the test samples, which of course we don't for the other approaches. And you see that here this is just using the mandatory constraints, and here just using the learned preferences, and really it's much worse than using both together to get the green curve. So if you want to know more about this learning approach and the theory behind, I invite you to see the talk by Schiex on Friday. Thank you.